All right, let's try an example for force balance, right? So we're going to balance our forces. We want everything to stay stable, right? And here we've got the closest thing to a figure I could find. I couldn't find a figure of one person and three kids. But that's basically what I want to look at in this tug of war. So this is supposed to be a rope. So we have cousin Ned, who's a college linebacker, and he's playing tug of war with the Murphy triplets, and there's some water, just to make life more interesting. And Ned, we know, can do 300 or 750 pounds of force. Actually, it should be something higher, I think. No, that's probably about right. He can push that or pull that, so he knows that because he does it all the time in camp. So in training, so how much can one of the triplets pull if they're equally balanced? So that's what we want to do. And the way we set things up here is first we draw stuff. So I put a picture here, but normally we draw something. We're not artists, so we'll just draw little stick figures. And if we are artists, then it's probably still better to do little stick figures because it doesn't do you any good to know what Ned's ears look like. So Ned is pulling his rope. The triplets are pulling their rope. He's pulling this way with a Ned force. Each one of the triplets are pulling to the right with the Murphy force. And so we're going to balance the forces. So that sort of tells us what's going on. We can make that a little easier. So what we usually do is we draw a box representing more or less, in this case, really it's representing the rope. Because it's the rope. If the rope moves, then the Murphys move, right? That's what we care about. So Ned is pulling on the rope this way. A nice big long arrow at 750 pounds. And then the triplets have 3 Murphys going to the right. Okay, so that's what we're looking for. And this is a force balance equation. So we can, basically what we do is we add these all up and we figure out what's going on. Now, Ned is pulling to the left. Left usually on a number line is negative, so we'll call that minus Ned, plus 1 Murphy, plus 2 Murphys, plus 3 Murphys. Going to the right, and these have to balance, so that's all equal to 0. All right? So we've got a balance equation right there. So we've drawn this little force figure, this force diagram. Always do that with a force problem. We'll do it over and over and over again for 14 weeks. And then when we have this force diagram, all we have to do is add up the little arrows, to get us the answer, right? This drawing and this equation, and the equations are what we have to work with in physics, are the same thing, basically. This is just a visual representation of this so that you can construct this. So when you draw this and you try to simplify it down into the force diagram and then put it into an equation, that's a process that will let you solve more and more complicated problems. This is pretty simple, but there are more and more complicated problems. You're never going to run out of complicated problems. Again, this is physics. We can make them as complicated as you want. Even in, Physics 1 context, we can make extremely complicated problems. They used to make really complicated problems for Physics 1. So we've got this system, right? And this is our force diagram. And that force diagram gives us this equation. So what do we want to do with that? Well, the first thing we can do is we know what N is, right? N is the Ned force, and the Ned force is 750 pounds. So that's minus 750 pounds of force, lbf. And then we have 3 Murphy forces going in the same direction. So m plus m plus m is 3m. That's all equal to 0. So now we're just doing math, right? It's algebra, but it's still math. What I'm going to want to do is I'm going to want to get the 750 on the right, because I want to solve for the Murphy force, right? That's what I care about. I want to figure out how much one of the triplets pulls. It's 1 Murphy force. So that means I have to add 750 pounds. Always keep your units. To both sides. So 750 minus 750 is 0. So we end up with 3m on the left-hand side is equal to 750 pounds on the right-hand side. So a really good video about physics problem solving called Read the... This is literally what it's called on YouTube. Read the effing problem. And this RTFP is a mnemonic for how to solve one of these problems. And it's a good video, it's a good way to solve problems. So I do suggest you look at it, kind of. It had one problem though, which is why I'm never going to link to it, is in solving the problem he dropped the units. And you'd never do that. Never do that. It's 2 points off. Every 15-point problem, if I see that happen, it's 2 points off. So don't do that, right? You'll always drop a letter grade if you do that in the class, and not just my class. So I do suggest you look at that, but be sure that you keep units. He's got some good advice. Now, we have 3m is equal to 750 pounds. Get rid of this by dividing by 3 on both sides, right? We want to have just m alone. When you have 3 times something, you divide by that on both, divide by that, and you get what you want. And because this is an equation, because 3m and 750 pounds are the same thing, whatever you do on the left-hand side, you have to do the right-hand side, right? You'll remember that, hopefully. I mean, I don't know how long it's been since you've had math. For some people, it's been a long time. So you divide by 3 on both sides, and then you divide by 3 on, right? So you divide by 3 here, that's m. You divide by 3 on this side, that's, let's see, 3 goes into 750, 250 times. So each of the Murphy triplets can do 250 pounds. Whereas their big cousin likes to tackle people in college can do 750 pounds. Sound reasonably reasonable? I think it's pretty reasonable. So that's sort of the process for solving one of these problems, right? Get your picture, translate the picture into a force diagram, then take the force diagram and turn it into an equation. After you've got that equation, right, which is just looking at the arrows here, and for each one of these arrows, you put it over here. If it's going to the left, it's negative. If it's going to the right, it's positive. Then you start substituting, right? So here we substituted something we knew up here. Probably I should do things a little more systematically for you, but usually that just makes people angry. And then I have a bunch of things that are the same, so I just give them a multiple. Then we do a little bit of algebra, a little more algebra, and we're done. So most of the algebra here is not so hard. Occasionally there'll be something that's more difficult, but most of the algebra is not very hard as far as algebra goes, right? The difficulty is moving from reading to the drawing, and from the drawing to the diagram. Right? So these are the hardest parts. It might take a little bit of getting used to going from the diagram to the main equation, but I think you can do that. That just takes practice. That's just practice. That's not something that requires any real insight, real thinking about the problem. But here we have thinking going on in these two steps. The drawing is a middle part to get you here, and you should always draw something. You should always draw something out, because drawing things is how you get the visuals in your brain, and that's how you start to translate this thing from an awful bunch of words into a physics problem. All right, so that's the first example of the course. I hope that seems not so horrible to you, and that you'll be happy enough with that. I'll come back a little bit later. I'm going to go work out. I'll come back a little bit later and I'll do another one for you, and then maybe I'll do two more for you, because the only thing I have after that is dinner. And then we'll go ahead and go on to the next lecture. So coming up is a rotational balance, right? So here we've got translational balance, that is in one dimension going this way. Next we're going to look at, keeping something, keeping a stick from falling, from rotating. We don't want it to rotate. So that's our next. I have no idea what that looks like. I don't know what you see. We're going to look at keeping things from rotating, right? So first we're keeping things from moving. Next we're going to keep things from spinning. Thanks. I'll talk to you in a few minutes. Bye now.